Hello, everyone, and welcome to this talk. Thanks for joining. I am proudly associated with Goethe University Frankfurt and FIES, but I would like to particularly thank the German Research Foundation, who has been paying my salary for many years now on a project-by-project basis, so sincere thanks. I also want to emphasize that I am aware that there could be many others here giving this talk now. And the reason why I'm giving this talk is because I've had many excellent collaborators on various aspects of this project. Nick Arndt, Axel Gerdes, Larry Heeman, Heidi Höfer, Vincenzo Stagno, Richard Stern, Farnus Viljoen, and Alan Woodland in alphabetical order. There were also those who have given me advice and opportunities: Thomas Stachel at University of Alberta, Bill Griffin and Sue O'Reilly at Macquarie University, Roberta Rudnick and Bill McDonough at University of Maryland, Steve Shirey at Carnegie Institution of Washington, and Rob Creaser again at University of Alberta. And then, of course, there was someone who thought it was a good idea to propose me. Before I get into it, I would like to share a fun fact, which is that Paul Gast was actually the primary supervisor of Bill Griffin during his PhD and early postdoc years, and Bill has some exhilarating stories to tell about this time. The term chemical geodynamics is borrowed, of course. Sindler and Hart write that it was developed by Allegre as an integrated study of the chemical and physical structure and evolution of the solid Earth. And what we would like to do is we would like to provide improved constraints on the physical-chemical parameters of the paleoconvecting mantle, which could be used to model Earth dynamic evolution through time. And so the four main topics I'm going to cover in this talk are the convecting mantle potential temperature, Tp, its composition, X, its oxygen fugacity, or FO2, and then I'm also briefly going to talk about the oxygen fugacity of subducted oceanic crust, the metamorphic product of spreading ridge derived basalt. Okay, here it is, an eclogite xenolith. It's a very pretty rock, sometimes diamondiferous, like this one here. But this simple mineralogy and almost innocent look belie a complicated origin and evolution, starting at paleo spreading ridges, followed by seawater alteration, then subduction, metamorphism, probably loss of a partial melt, before incorporation into the cratonic lithospheric mantle, where eclogite might be exposed to metasomatism, and then finally, billions of years later, exhumation with kimberlites. I need to clarify that when I talk about now about the convecting mantle or ambient convecting mantle, I mean the one underlying spreading ridges, typically. I do not include thermochemically anomalous mantle that is sampled by plumes. Also, I'm not going to argue for the purpose of this talk that eclogite xenoliths actually have mid-ocean ridge protolith, and I'm also going to take it for granted that we've had full-fledged plate tectonics since at least 3 billion years ago. Of course, in combination, these two things have for a long time, for decades, been used to argue that eclogite xenoliths indicate Archean subduction or even plate tectonics, that they have a link to continental crust formation via loss of a silicic melt, and also that they indicate that cratons grew during collisional processes. And I guess the novelty of what we've been trying to do is to peer through all these processes into the ambient convecting mantle source, which is admittedly pretty crazy. So why bother? Take modern mid-ocean ridge basalt, for example. It forms from the ambient convecting mantle beneath spreading ridges, and it is therefore able to give us information on the composition, temperature, and oxygen fugacity of the modern convecting mantle. However, when you consider this map of seafloor ages, you can see that after a few 100 million years at most, oceanic crust is subducted. And so we have to look for other samples of paleo convecting mantle. That could be, for example, tectonically exhumed eclogite or ophiolites. However, such rocks become increasingly rare and also controversial as you go back in time. In contrast, as I mentioned before, eclogite xenoliths have long been recognized as forming in spreading ridges. They have Archean to Paleoproterozoic metamorphic ages, and therefore they can provide us with information on the composition, temperature, and oxygen fugacity of the paleoconvecting mantle. And we care about these parameters because they critically affect, for example, melting relations, crust mantle evolution, the viability of plate tectonics, or the nature of volcanic gases that are released from mantle-derived magmas to the atmosphere ultimately, among many other consequences. And so how could we, for example, determine oxygen fugacity and temperature? For oxygen fugacity, we can use the speciation or partitioning of redox-sensitive elements. And this is a plot of ferric over total iron ratio on the left and of bulk distribution coefficient as a function of oxygen fugacity relative to the firelight magnetite quartz buffer. In glasses, ferric over total iron ratio increases with oxygen fugacity, not unexpectedly. The bulk distribution coefficient of the homovalent element scandium does not change with oxygen fugacity. However, vanadium becomes increasingly incompatible during mantle melting. And so we can exploit these relationships to obtain oxygen fugacity estimates. Mantle-derived melts have also for a long time been used to obtain insights into mantle potential temperature, exploiting, for example, the sensitivity of MgO, or also of melt fraction, which varies as a function of depth or temperature of the onset of partial melting. And so, of course, there have been various estimates of oxygen fugacity based on ferric over total iron ratio, but also based on vanadium. And these differ by about a log unit. Similarly, for potential temperature, there's various estimates, and the difference is about 100 degrees Celsius for the modern ambient convecting mantle. And so this variability might reflect a variety of true source heterogeneity, but also the nature of the samples or effects of various processes or methodological bias. And if it's true for the modern mantle, it's certainly true also for the paleoconvecting mantle. So what can we do to constrain TP from eclogite? This exploits the observation that the concentration of a moderately incompatible element in the melt, such as titanium or samarium, decreases with increasing melt fraction F. And so when you look at this schematic diagram of pressure versus temperature, you can see that an upwelling parcel of mantle would intersect the mantle solidus at a certain pressure, where it starts to partially melt. That's the initial pressure of partial melting. And then in spreading ridges, it can decompress all the way to about 0.5 GPa, where melting stops. You can also appreciate how, as you increase potential temperature, you can intersect the mantle solidus at greater depth and higher pressures. And so you have more decompression melting, giving rise to higher melt fractions. And so what we do is we use titanium or samarium abundances and the batch melting equation to obtain the melt fraction, and then via several relationships then finally arrive at the mantle potential temperature. And when we do that, and we, or before we do that, we have to actually take care of the several steps in the evolution of mantle eclogite. And so to avoid kimberlite contamination, which is ubiquitous, we can use mineral compositions weighted by their modal abundances. And the good news is that samarium and titanium have distribution coefficients between eclogitic garnet and CPX close to 1, which means that the contributions from uncertainties in modal abundances is relatively small. Conversely, rutile is, of course, as pure titanium dioxide, makes a difference, and we can estimate its modal abundances assuming that the bulk rock has no titanium anomaly, as is probably true for relatively dry peridotite melting in spreading ridges. There's a variety of elements we can now use as indicators of mantle metasomatism, and so we can recognize samples and exclude those from further consideration. We have to take care of partial melting of eclogite during subduction. Seawater alteration is typically monitored with oxygen isotope compositions, and it never shows any variation really. Accumulation is important because if you have accumulation of olivine and plagioclase, for example, the incompatible elements titanium and samarium would have relatively low abundances, and so we can recognize and filter the samples based, for example, on the size of the europium anomaly or based on aluminium over iron oxide ratios. And then finally, low pressure differentiation, especially the fractionation of olivine, has to be considered. And so these two processes are now looked at with more detail, starting with olivine fractionation. And this is a plot showing titanium and samarium as a function of MgO content. And for a picritic precursor, a protolith with about 17 weight % MgO, we can model the concentrations of major and minor elements using the MELTS software. And you can see that so long as only olivine fractionates here, there's relatively little change in titanium concentration. Similarly, for samarium, we can model this using trace element modeling, and the change in samarium concentration is relatively modest, so long as we look at samples with high MgO content. Looking at partial melt extraction from eclogite, we can model this, for example, as a melt with a melt fraction of 0.3, with a starting composition of 10 weight % MgO and a certain amount of titanium and samarium. And experimental melting residues demonstrate that the change in titanium concentration is relatively minor. Also, the bulk distribution coefficient for samarium is close to 1, which means that melt extraction results in little change in samarium concentration. So we can overlay finally our samples, and I would like to emphasize these have been filtered to exclude those with cumulate protolith, those that have been recognized as metasomatized. They are only high MgO samples that have not experienced clinopyroxene accumulation or fractionation, or had pyroxenite in the source according to equations given in Herzberg and Asimov. And then for each locality, we only use those with the lowest concentrations, which would result in the highest melt fractions and temperatures. So finally, when we do so, and we only use samples with recognized oceanic crustal protolith, encompassing not only xenolith, but also orogenic eclogite and some ophiolites, these red dots show where the results plot. They are fairly similar to a potential temperature evolution curve from Davies 2009 based on a parameterized convection model. Also much earlier constraints and also more recent constraints based on natural samples. And they are more different from a hot mantle potential temperature evolution curve of Herzberg et al., which shows a maximum in Meso and Neo-Archean time. We've applied the same modeling just now to a parental MORB estimate by New and O'Hara, and we come out at about 1300 degrees Celsius, which is also similar to other estimates. I have to emphasize, though, that the underlying assumption of a correspondence between melt fraction and potential temperature breaks down as we get into higher pressures, where Garnet starts to be important. Also, as all modeling, of course, the results are dependent on the input. And so if the source concentration was higher, if the bulk distribution coefficient was lower, if the final melting pressures were higher, or if we had some unrecognized cumulates, as an example, then all this would result in higher potential temperatures. This here shows an example of such effects. It's the same curve with our preferred model for a depleted mantle source, again in blue. And the purple dots show the TPs for a depleted mantle that formed 3.5 billion years ago from a primitive mantle source and then linearly evolved with respect to composition to modern values. And so as you go back in time, the source concentration increases, and so the potential temperatures become higher. And so while you could absolutely argue with the input and the modeling and the parameters, I think that the result is really fairly robust, that we've had monotonous cooling and that we have not had a maximum at Meso or Neo-Archean time. Now, looking at some consequences, if we take the temperature, for example, at 3 billion years ago, and we recall that delta T is the difference between an ambient convecting mantle and that a certain time ago, we can compare these results, for example, to what Sisova et al. Modeled in 2010 regarding the viability of subduction as a function of delta T. And for a hot model, we'd be in a regime where we cannot have subduction, or at most a pre-subduction regime. Whereas for a warm model, we would have modern-like subduction and probably full-fledged plate tectonics. We can also look at effects of potential temperature on the percentage of continental area emerged above sea level. This shows a contour of constant continental freeboard for present-day hypsometry. And this plot illustrates the dependence on of continental freeboard and continental area on TP. And of course, if in the Archean the hypsometric curve was flatter, then this would diminish the percent continental area that could be emerged. But regardless, we can see that for a hot model of potential temperature evolution in the Archean, we couldn't have any emerged continental crust. Whereas for moderate temperatures, we could have at least some continental freeboard and emerged continental area. And so it's incredibly important to constrain this parameter. And if TP in the Archean really was moderate rather than hot, it would allow early establishment of a sustained plate tectonic regime with all the consequences, such as the evolution of the geochemical reservoirs, but also impacts on where and how devolatilization reactions happen upon subduction. It would allow for some emerged continental crust and therefore continental weathering, which has immense consequences, for example, for enhanced nutrient delivery to the oceans, which then affects biomass and O2 production. Next, I would briefly like to delve into the degree of mantle depletion. We have a preferred model. We say in the Archean, the mantle was depleted. Already there was a depleted mantle reservoir. And doing that allows me to also show some strontium isotope compositions, which I think is fitting in a Paul Gast lecture. And what you see here is a plot of strontium isotope composition in clinopyroxene as a function of the size of the europium anomaly, which is a proxy for the volume of plagioclase that formed during accumulation in the low pressure stage. And you can see how there is a general tendency that the samples with the strongest cumulate character have the lowest strontium isotope compositions, which is totally consistent with stronger exclusion of rubidium than strontium in olivine plagioclase-rich cumulates. And so, of course, this is what we see in modern gabbros. There is an anti-correlation of rubidium strontium with the size of the europium anomaly. And if we calculate back strontium isotope compositions to the initial ratios based on known eclogite ages of 3 and 2 billion years roughly, respectively, we can see that there are several suites in the Archean that are depleted relative to estimates of the bulk silicate Earth, and certainly the Paleoproterozoic one is depleted relative to bulk silicate Earth 2 billion years ago. And so I think this allows the conclusion that the ambient mantle was at least partially depleted in the Archean. The next big topic is oxygen fugacity. And it's the same spiel as before. Now we're looking at vanadium. We have to take into consideration all these various steps. The difference is that now vanadium is 3.5 times more compatible in clinopyroxene than in garnet. And so uncertainties in modal abundances play a greater role. Conversely, the rutile contribution to the vanadium budget remain small, mainly because the rutile abundance is small. We take into account all of that and now look straight at the effects of partial melt extraction and low pressure differentiation. This here shows a plot of vanadium abundance as a function of MgO content. Again, for an eclogite with 10% weight MgO, and you can see how MgO increases relatively strongly, and the behavior of vanadium depends on the oxygen fugacity. So if conditions are relatively reduced at FMQ-2, vanadium would behave mildly compatibly, whereas at FMQ it would behave mildly incompatibly. But the changes here are relatively modest. I have to say also that these modeling results are semi-quantitative because we actually don't yet have models for the pressure, for the temperature and FO2 dependent partitioning of vanadium between eclogite, garnet, and CPX and the silicic melt. Conversely, thanks to the work of Wang et al. In 2019, we can model the concentration of vanadium in a melt as a function of both temperature and oxygen fugacity. We have our starting composition, and we can see that for a mantle potential temperature of 1450 degrees Celsius, at about a melt fraction of 0.2, we get initial vanadium concentrations which decrease as conditions become more reducing, and this is because vanadium starts to behave less incompatibly as oxygen fugacity goes down. And then from that starting composition, so long as we have only olivine fractionation, the change is relatively modest again. This gray envelope here actually shows the effect of temperature. Vanadium becomes more incompatible as it becomes hotter, and so changing the temperature by about 50 degrees would result in this curve to be shifted upward, and then with a relatively larger proportion of samples shifted below this curve, as an example. Now, looking at actual samples, these here have again been filtered to exclude cumulates and those that have been metasomatized. And we can see that, or I hope you agree, that most samples in the Archaean here actually plot between FMQ-1 and FMQ-2. There are some that go off to higher vanadium concentrations. For the Paleoproterozoic suite from the slave craton, most oxygen fugacities are actually higher. And we have now harvested the vanadium abundances reported for inclusions in diamond. The idea is that these inclusions behave as closed systems after encapsulation, whereas the eclogite xenolith remained an open system. And there's few data, admittedly, that pass through the filtering. And these show actually no systematic difference between the inclusions with field symbols and the xenolith. And I think this means that there has been no systematic change to the eclogite reservoir with respect to vanadium concentrations. And so I would like to invite you to look at material uploaded for this flash presentation, which is the very last one tomorrow evening, which shows more of the results for the inclusions versus xenolith with some very interesting systematics. Altogether, I think these results support earlier suggestions that there has been an evolution in oxygen fugacity in the ambient convecting mantle. When we look at this plot of oxygen fugacity versus age, we are trying to get from a very reduced conditions right after core formation to the modern convecting mantle somewhere up here. After the magma ocean stage, the oxygen fugacity is permissive of a range of scenarios. But I would argue that I think samples suggest that there really has been an evolution across the Archaean Proterozoic boundary. And this is for two completely different sample types. Niklas et al. Looked at komatiites, pygrites, and basalts, and they used olivine melt distribution coefficients to extract oxygen fugacity, whereas we used eclogites and vanadium, scandium compared to forward models to extract oxygen fugacity. And while there is an offset, the relative difference is very similar. I would like to add here that Steve Foley in 2011 already predicted the Archean mantle to be more reduced, and he suggested that eclogite xenoliths can provide useful results. And so this is actually what got me started on this whole thing. And so if the Archean ambient mantle really was more reduced, it would have implications for melting relations. For example, metal saturation and redox melting would occur at shallower depths. It would be permissive of a role of mantle oxygen fugacity in the great oxidation event, shown here in blue. And you can see the change across this boundary. Also, if from this reduced gases in Hadean and Eoarchean time, methane was formed catalytically, for example, this could alleviate the faint young sun paradox, and it would generate a productive atmosphere in terms of evolution of life right here on Earth. As a very final brief topic, I would like to get into the oxygen fugacity of subducted oceanic crust, that is eclogite, the metamorphic product. And for a few years now, thanks to Vincenzo Stagno and others, we can now apply an oxybarometer to eclogite. It's based on an equilibrium between eclogitic minerals. So we are now looking at the metamorphic product, no longer trying to go back into the convecting mantle. When we apply this barometer to eclogite xenolith, we can see that oxygen fugacity as a function of depth, there is a huge range, and most eclogite xenolith here from the Kapwal craton, but also representative of other cratons. Most samples fall below FMQ -1. I would like to highlight that prograde orogenic eclogite from the Tian Shan, which is a phanerozoic orogenic eclogite, also is relatively reducing. Now, when we look at these results, we can say that the vast majority of eclogite is not stable with carbonatite or with carbonate minerals, but it is stable with graphite and diamond, and this is exactly what we observe also in the samples. There isn't even a width of oxidized sulfur in a melt in equilibrium with these samples, and fluids would be probably methane dominated. And so I would like to emphasize that subducted oceanic crust that has not been modified on subduction by interaction with palite and so on, was strongly seawater altered, adds no positive redox budget to either arcs or the deep mantle. And so now I would like to finish with some provocative statements. The Archean ambient convecting mantle was partly depleted. It was only 100 to 150 degrees warmer. It was more reduced than the modern mantle by about 1 to 2 block units. And both ancient and modern subducted oceanic crust are relatively reduced. And with that, I would like to thank you for your attention, and I look forward to a lively discussion. Thank you.